So as promised, we're going to start with the cosine function and go through all the rest of the trig functions and develop our rules. And therefore, we don't have to do definition, derivative, of anything anymore because it'll be nice and simple from there. So let's start with the same sort of analysis, because I always like to start with a graphical analysis because it reminds us what the derivative really is, right? So if I've got this, once again, let's demarcate out those, and that's pi over 2, right? So let's do that up here, pi over 2, pi, 3 pi over 2, 2 pi, right? 1, -1, and so we know that the cosine function does following, which is a lot better than my sine function that I made in the last video. So here's going to be my f prime of x. I want to get the demarcations nice and simple there. Perfect. And so here I go. What can I say? Well, if we just continue the path just a little bit there, we can see that I have zeros at those points. So 0, 0, 0. Here I have my negative max, whatever that negative number is. I don't know what it is, but I know it's a negative max. And here I have that positive max. And I know it's just as positive, this is negative. And so then I can do my same analysis here to know it's not straight lines. In the first half of this domain, there's quite a bit of change of slope. And the second half of the domain, it's almost like locally linear, so there's not a lot of change in slope. So in other words, we're going to change from 0 down to a large negative slope, so a large negative number on this graph, becoming just like not much change in the slope. Then going from here to here, in the first half of the domain, there's not a lot of change in slope, but then it goes very quickly to 0, boom, and then from there I can talk about symmetry, and there we go. So it looks like, well, what graph do I have here? Well, it's not a sine function, it's a negative sine function. It's shifted over. So there we go. So that's what it looks like. I don't know if that's true. I'll have to prove it. How are we going to prove it? Of course, definition of the derivative. But we've done so much of the prep work that this is going to be so much easier this time. So if y is equal to cosine of x, then dy dx, we're going to go right into the definition of the derivative. Limit as delta x approaches 0 of cosine of x plus delta x minus cosine of x all over delta x. Once again, indeterminate form, no bueno, so we need to transform it, limit as delta x approaches 0, and I gotta expand this, yay, for our trig identities. So that's cosine of x times cosine of delta x minus, because remember it flips the sign, so annoying there, sine of x cosine of delta x minus cosine of x all over delta x. Now, leaning on what we saw in the last video, we want to do that same grouping and distribution of the limit. So I've got a group by cosine and by sine. So here we go. So I'm going to pull the cosine of x through the limit, because remember, the limit acts on the delta x terms, not on the x terms. So this is limit of delta x approaches 0 of, and what do I have left here? I've got cosine of delta x minus 1 over delta x. And then I've got left here negative sine of x, because I'm going to pull the negative sign through the limit as well, just to make my life a little bit easier. Delta x approaches, limit as delta x approaches 0 of, in this case I've got, oh, sorry, this should be a sine. I'm like, what did I do wrong? Sine of x, delta x over delta x. Now, we've already done these limits. We know, so I can just lean on that this goes to 0, and this goes to 1. And so just very quickly then, I can see that the derivative of cosine of x is negative sine of x. There you go. That is my next derivative rule. Derivative of cosine of x with respect to x is, actually let me write it the way I like it, the derivative with ddx of cosine of x, showing the operator acting on the function, is equal to negative sine of x. Boom, there's our rule. Right? Our graph supported that, and the definition of the derivative kind of made it all perfect. So now, what about the rest of them? Well, let's do the next easiest one, which is tangent. So y is equal to tangent of x. So just thinking about the graph of tangent of x, let's just talk about what's got to be true about the derivative of tangent of x. So here we go. If this is y and this is x, actually it probably should do just a little bit here. We know that this graph looks like this. And it's got asymptotes. Every at pi over 2, 3 pi over 2, negative pi over 2, etc., right? This graph has a very specific periodicity, and it's got asymptotes at a very periodic way as well. So that's what that graph looks like. So let's talk about what the function's got to be that describes the slope of this. The first thing that we notice here is that the slope will not exist at negative pi over 2, pi over 2, 3 pi over 2, etc. Meaning where the asymptotes of this graph are have to be at the same place as the asymptotes of the graph that we're about to derive. It's got to be, otherwise it won't work. So that sort of lends credence to our thought from the other day that the periodicity of the graph is going to remain the same, right? So whatever the periodicity of the tangent function is going to be the periodicity of the function that is its derivative. The second thing I want you to notice here is that the slope is always positive, right? No matter what. And what that slope is doing here is that slope goes from positive infinity down to 0, back to positive infinity, right? So first that slope is decreasing, and then that slope is increasing. That slope is getting less steep, then it's getting more steep. Now remember, decreasing and getting less steep don't mean the same thing. Decreasing means going from positive infinity down to negative infinity. Here, that just correlates with getting less steep, right? So there you go. So I need a function that does all of those things. Great, so here we go. Now, what we're not gonna do here, what we're absolutely not gonna do here, because it would just be terrible, oh, actually, not down to 0. I don't know that that's 0. Down to some number. I'll just say some sort of positive constant. I just assumed that's 0, but that doesn't mean the slope at that point is 0. It might not be flat there. It could be whatever it is. My bad. So what are we going to do from here? Well, I certainly don't want to do definition of the derivative here, because if you think about it, when we did definition of the derivative with sine of x and cosine of x, we ended up with sine of a plus b and cosine of a plus b. Have you ever looked at the tangent of a plus b? That equation's a train wreck. I don't want to deal with that. That's not going to be easy. So instead, what do we do when we have a function that looks difficult? Well, what we do is we write it. Tangent of x is equal to sine of x over cosine of x. I have rules for both of those. And guess what? I don't like that either. This is sine of x times cosine of x to the negative 1. So what do I have? I have a product rule. Nice and simple. So d dx. d dx of tangent of x. It's the first function, sine of x, times the derivative of the second function, which is cosine of x to the negative 1. So I have a product rule for functions there. Nothing changes about our format or our process just because we're dealing with transcendental functions. Great. So I've got sine of x, and then brackets, negative 1, cosine of x to the negative 2, and then the derivative with respect to x of cosine of x. Okay? Right? And then plus cosine of x to the negative 1, and then derivative of sine of x we know is cosine of x. Well, that's convenient. Cosine of x to the negative 1 and cosine of x, that whole term goes to 1. So what do I have here? I have sine of x, brackets, negative 1. I've got cosine of, that's gross. So I'm just going to actually put that as 1 over cosine of x squared. And then the derivative of cosine of x we know is negative sine of x from the work we did before. So there we go. So let's look at this. Negative and negative is a positive, sine of x, sine of x. So I've got sine squared x over cosine squared x plus 1, which of course is tangent squared x plus 1. And hopefully something in your brain's going, I know that, I know that, I know that. What's that? That's secant squared. Now, if you don't remember that, remember that you can always go sine squared of x plus cosine squared of x is equal to 1. If I divide both sides by cosine of x, I end up with sine squared of x over cosine squared of x plus 1 is equal to 1 over cosine squared of x, and that's, of course, tangent squared, and that is secant squared. So I got a rule now. The derivative with respect to x of tangent of x is equal to secant squared of x. Boom. Awesome. So next, let's tackle the secant. The derivative with respect to x of secant of x. Well, actually, hold on a second. Whoa. Let's go back to our graphical analysis. Secant squared of x, does that obey the same thing? Well, first off, yeah, because very simply, I know that the secant graph has asymptotes at the same spot. But what does the secant graph look like? Well, the secant graph normally, let me just draw this on the side, looks like a series of sort of U's, like this, right, that alternate up and down, right? But that's not what we need, because now the slope is always negative. That means that these don't exist. Oh, hold on, it's secant squared. That flips each of these up into the top quadrant here, so I end up with graphs that look like this as a derivative. The slope does not exist at the asymptotes. Beautiful. The slope is always positive. Here, the value of the function then is always positive. Awesome. And the slope, meaning the value of this function, goes from positive infinity down to some constant and back up. Boom. We actually now know that the slope at this point is 1 because I know the value of the secant function at 0 is equal to 1. So brilliant. It just totally correlated with everything that we need. So I'm just going to do the secant graph, the secant function here. The way we're going to do this is we're just going to make our lives a lot simpler. And we're going to rewrite this as d dx of cosine of x to the negative 1. Now, if you remember, folks, we just did that. That's this term here. So that means that this is the derivative of the secant. So what do I have there? Well, apparently I have a positive, negative of sine of x over cosine squared x. Yes? But that's gross. Let's rewrite that. That's sine of x over cosine of x times 1 over cosine of x, okay? Which is tangent of x secant of x. And there you go. There's your answer. The derivative of the secant function of x is equal to tangent of x secant of x. That's sort of a weird result if you think about that in a way, because it says that the derivative of the function, the slope of the function, depends upon the value of the function at that point. Isn't that fun, right? So whatever the value of the secant function is affects the value of the slope of the secant function at that point, times also what the tangent of that value would be at that point, which is fun. So now, just to kind of like put together what we have here, I have the derivative of sine of x with respect to x is cosine of x. I have the derivative with respect to x of cosine of x is equal to negative sine of x. All right. The next thing I have here is the derivative with respect to x of the secant of x is equal to tangent of x secant of x. And I have the derivative with respect to x of, of tangent of x is equal to secant squared of x. So the only two things I have left are the derivative of cosecant of x and the derivative of cotan of x. And I think you can see how you would do those, right? We would turn the cosecant of x into sine of x to the negative 1. We turn cotangent of x into cosine of x over sine of x and do the same process. But let's actually look at some patterns here. Notice here, it seems like when we have a cofunction, two things are true, right? That the derivative of a cofunction has to do with the other, its cofunction mate. Sine becomes cosine, cosine becomes sine, right? So it would stand to reason that if I've got secant becomes tangent secant, that there's going to be a similar sort of pattern here, but it's going to become the cofunctions of it, right? So cotangent x, cosecant x, same structure, just the opposites, right? The cofunction. So then cotangent of x should become cosecant squared x. Now, the next thing is, notice the derivatives of all the regular functions are positive, but the cosine function, the cofunction, has a negative. So that would stand to reason that we would have a negative sign there. And actually, these are the right derivatives. Now, if you don't trust the analysis that I did, you can do as I said and do the derivative of sine of x to the negative 1 and show that you come out with this, and do the derivative of cosine of x times sine of x to the negative 1 and show it comes out to this. But I wanted to show you that there are indeed patterns involved in the way that happens because of the geometries and the symmetries involved in the sine and cosine functions and the regular functions and the cofunctions. So there you go. Those are your trig rules.